All right. Hey, everybody, it's Miss Davis. This is my first Ed Puzzle in biology ever, and I'm really excited to be sharing with you and starting with you for the next 8 weeks. So bear with me. We're learning together, and we're learning lots, and I'm really excited, so I hope you guys are too. The first idea that we're talking about during this unit on evolution is where and how life begins. So remember that Miss Bonert had talked about Remember what Miss Bonert had talked about, that evolution is different than beginning of life. Evolution is change over time. So evolution is not really religious or versus science kind of a topic. Now, the origin of life, that brings some of that in. So we're going to talk about the scientific perspective here, and we can have a good, well-rounded conversation about this together. But right now I'd like to share with you just the topics based on science. So where and how life begins, this is the scientific perspective. So there are two ideas here. First, there is the spontaneous generation. Something comes from nothing. Living can come from non-living. There's a vital force in the air. This was the centuries. And then you have now this biogenesis, that living can only come from living things. Now, this image over here is an image that describes the Big Bang Theory. Now, the Big Bang Theory is an effort to explain what happened in the very beginning of the universe. Discoveries in astronomy and physics have shown beyond a reasonable doubt that our universe did, in fact, have a beginning. Prior to that moment, there was nothing. During and after that moment, there was something, our universe. The Big Bang Theory is an effort to explain what happened during and after that specific moment. So according to the standard theory, our universe sprang into existence as singularity about 13.7 billion years ago. So right around here. What is a singularity and where does it come from? Well, to be honest, we don't know for sure. Singularities are zones which defy our current understanding of physics. They are thought to exist as the core of black holes. Black holes are the areas of intense gravitational pressure. The pressure is thought to be so intense that finite matter is actually squished into infinite density. That's a mathematical concept which truly boggles the mind. These zones of indefinite density are called singularities. Our universe is thought to have begun as a really, really, really small, infinitely hot, infinitely dense something, a singularity. Where did it come from? We don't know. Why did it appear? We don't know. After its initial appearance, it apparently inflated. That's the big bang. So it's not an explosion, it just inflated, it expands. So it expanded and cooled, going from very small and very, very hot to the size and temperature of our current universe. It continues to expand and cool to this day, and we are inside of it. Incredible creatures living on a unique planet, circling a beautiful star, clustered together with several hundred billions of other stars in a galaxy soaring through the cosmos, all of which is inside of an expanding universe that began as a very, 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 very small singularity, which appeared out of nowhere for unknown reasons. This is Big Bang Theory. So there are some common misconceptions about the Big Bang. For example, there was no explosion. It's an expansion. Another misconception is that we tend to imagine the singularity as a little fireball appearing somewhere in space. According to the many experts, however, space didn't exist prior to the Big Bang. Back in the late 60s and 70s, when men first walked upon the moon, 3 British astrophysicists, Stephen Hawking, George Ellis, and Roger Penrose, turned their attention to the theory of relativity and its implications regarding our notions of time. So in 68 and 70, they published papers in which they extended Einstein's theory of general relativity to include measurements of time and space. According to their calculations, time and space had a finite beginning that corresponded to the origin of matter and energy. The singularity didn't appear in space, rather, space began inside of the singularity. Prior to the singularity, nothing existed. Not space, not time, not matter, not energy, nothing. So where and in what did the singularity appear if not in space? We don't know. We don't know where it came from, why it's here, or even where it is. All we really know is that we are inside of it, and we at one time didn't exist, and neither it didn't exist, and neither did we. So is the Big Bang Theory the only plausible theory? No, it's just the most popular one. Internationally renowned astrophysicist George F.R. Ellis explained, people need to be aware that there is a range of models that could explain the observations. For instance, I can construct you a spherically symmetrical universe with Earth at its center, and you cannot disprove it based on observations. You can only exclude it on philosophical grounds. In my view, there is absolutely nothing wrong in that. What I want to bring into the open is the fact that we are using philosophical criteria in choosing our models. A lot of cosmology tries to hide that. So in any discussion of the Big Bang Theory, there is religion that comes up. What about God? This is because cosmogony, the study of the origin of the universe, is an area where science and theology meet. Creation was a supernatural event. That is, it took place outside of the. This fact is the question, is there anything else which exists outside of the natural realm? Specifically, is there a master architect out there? We know that the universe had a beginning. Was God the first cause? We won't attempt to answer this question in class, but that is where I just wanted to point out that that is sort of where theology and science meet. That's where the discussion kind of comes together. So that was a really long slide on the Big Bang Theory. Sorry about that. Here is a short video to give you more information on the Big Bang Theory.
For centuries, the fact that we can discover things about the universe has really been something of a mystery. Why would beings like ourselves be able to discover a universe like this? Why is what we think about the universe, why would it correspond to the way things really are?
Our ability to discern and understand the universe is a fundamental part of what makes the universe tick, so that we're linked into it. This isn't just a sort of an accident, a trivial little byproduct. It is something that is linked to the great cosmic scheme of things. Now, I've no idea how that linkage works, why it's there, or anything of that sort, but I'm very, very struck by the fact that we can understand the universe in such exquisite detail and at such a deep level.
The spectacular progress of modern astronomy and physics is the product of a universe accessible to the human eye and mind. It is a universe governed by laws and forces that literally hold our planet Earth and the entire cosmos together, and are finely calibrated to allow for both complex life and scientific discovery.
If you didn't have something like gravity that pulled matter together, you would never get planets, you wouldn't get stars, you wouldn't get any complex organisms. If you didn't, there would be nothing to hold protons and neutrons together in the nucleus. And so you wouldn't have any atoms, so no chemistry. If you didn't have the electromagnetic force, you would have no bonding between chemicals. You'd have no light, and the list goes on. So you need all these sorts of fundamental principles have to be in place in order for life to occur. Wipe out one of those principles, wipe out one of those laws, no life.
During the past 40 years, scientists have determined the relative strengths of each of these primary laws and forces. These strengths are so critically balanced, they are often described as being finely tuned.
If you were to take the basic fundamental constants of nature and you were to change these even slightly, or you were to pick their values at random, you would almost never get a universe that would be habitable in any sort of way. That is, you couldn't have galaxies, you couldn't have planets, you couldn't have complex biological organisms if these fundamental constants were even slightly different, slightly stronger, slightly weaker than they actually are in this universe. That's the idea of fine-tuning.
To better appreciate this concept, imagine a machine able to control the strengths of each of the physical constants. If you changed even slightly from its current setting, the strength of any one of these fundamental forces, such as gravity, the impact on complex life would be catastrophic.
If you increased it by a little bit, no large-scale life forms could exist. Anything that was more than the size of a pea would be completely crushed. So you might be able to get life of a very, very primitive sort, such as bacteria, but you could never get conscious observers.
This is one of a long list of properties in underlying physics that seem to be prerequisites for a universe with life. For example, the strengths of the other forces of the various subatomic particles. If all of these things were even a little bit different, then life, certainly life as we know it, could not exist.
These forces and constants are another example of the correlation between life and discovery. For not only are they finely tuned for our existence, they can also be understood.
It's remarkable how well the laws work. And not only that, it's remarkable how simple they are. And that also is related to the discoverability of the laws.
Albert Einstein wrote, "I have deep faith that the principles of the universe will be both beautiful and simple." For nearly 400 years, scientists have discovered an elegant simplicity in the mathematical equations that express and unlock the laws of the cosmos.
It's been said that many of the most important theories in theoretical physics can be written on a single sheet of paper. And this, I think, ought to be considered surprising, that such a simple formula or equation could have such far-reaching applications to a very complicated and very large universe.
What you have is a universe that is not only finely tuned for life to occur, but also has a beautiful, elegant mathematical structure, and a structure such that we can discover that structure.
Most scientists just take it for granted that the world is both ordered and intelligible. And the intelligible part I find really quite extraordinary, because it's one thing to accept that the universe is ordered, but ordered in a way that human beings are capable of understanding is an extraordinary thing. And so the question naturally arises, what is the explanation for that?
Many who have pondered this mystery of an intelligible universe argue that it cannot be easily explained away.
From naturalistic assumptions, you would not expect the universe to be understandable by human reason. After all, within the standard naturalistic story, human reason was developed to be able to hunt prey, get around in the everyday world, attract mates.
We have certain skills, for example, we can jump streams and catch falling apples and so on, which are necessary to getting by in the world. But why is it that we also have the ability to discern, for example, what's going on inside atoms or inside black holes? These are completely outside the domain of everyday experience, totally surplus to requirements, not at all necessary for good Darwinian survival.
Discoverability of the universe is something we didn't need for our existence. It's something additional to it. It seems then that whatever the source of the universe is, it intended that it contain observers who can discover.
All right, so let's talk about some scientists and their experiments. The first one we have here is Reedy. And I'm not sure if I'm saying these names right, so that's okay with me. Let's see. Here we go. So for centuries, people have believed that living things could appear spontaneously from non-living things. For example, they noticed that frogs seemed to appear in the mud that was left after a river flooded. But when the soil dried, there were no frogs around. They concluded that muddy soil gave rise to frogs. Similarly, they noticed that mice seemed to appear when stored grain got moldy. So they concluded that moldy grain gave rise to mice. In 1668, an Italian physician named Francesco Reedy did an experiment that showed that maggots did not come from rotting meat. As was previously thought, he placed a piece of rotting meat in an open container and another piece in a closed container. He showed that maggots only grew on the meat in the open container of, he concluded in the open container. Since he had also noticed flies buzzing around the open container of meat, he concluded that the maggots were from the flies. People still did not totally abandon the idea of spontaneous generation. Instead, they began to believe that larger organisms did not arise spontaneously. But microorganisms did. In the mid-1700s, a Scottish scientist claimed that all inorganic matter had a life force that allowed microbes to grow. He demonstrated this by showing that soup exposed to air eventually grew bacteria and fungi. Needham even went so far as to briefly boil some soup, presumably to remove the microbes already in it, and poured it into clean flasks sealed with a cork. He still saw microbes growing, which he took as proof of his life force theory. "20 years later, an Italian biologist named Lazzaro Spallanzani tried to show that Needham was wrong. Spallanzani thought Needham's experiments were incomplete, that Needham did not boil the soup long enough to kill all the microbes, and that the cork seals were not airtight, which allowed microbes in the air to settle on the soup in the clean flasks. He made 2 batches of soup, one that was boiled for a few minutes like Needham's, and another that was boiled for an hour. The soup boiled for an hour was poured into a flask that was melted shut so nothing could get into the flask. Spallanzani found that this soup stayed sterile. The soup, boiled for a few minutes, then sealed in a flask with its mouth melted shut, did not stay sterile. Microbes grew in a few days. Spallanzani believed this proved that boiling for a few minutes was not enough to sterilize the soup. This meant Needham's experiments were flawed from the beginning. In addition, Spallanzani poured some of the soup that was boiled for an hour into another flask and then sealed it with a cork, like Needham did. He noticed that this batch grew microbes as well, suggesting that the microbes could get into the soup through the cork. So then in 1859, you have Louis Pasteur. Pasteur is, if you recognize Pasteur, Pasteur is like pasteurized, so pasteurization. This experiment finally proved that you could block off the microbes in the air, killing bacteria and keeping things safe inside of those jars. Then you have Urey and Miller experiment in 1950. This simulated Earth's early atmosphere in a glass tube setting, showed that organic matter could be created under certain conditions. He tried to show that using lightning, you could turn water into non-organic gases, with non-organic gases into water that has organic gases. All right, so I've given you a lot of information, a lot of scientists, a lot of theories, a lot of ideas. What I'd like to do now is for you to do some research on your own and possibly create an experiment that we can do. We can all see the effects, or we can see kind of an example of what those scientists were doing. But we're going to do some background research. You're going to choose a scientist, either someone that was mentioned in the video, either someone mentioned in what I was talking about, or directly from one of the slides. Choose your scientist. Decide what their experiment was. You can explain it with a diagram, or if possible, recreate the experiment. Some of these experiments are super simple that you can show sort of science fair style. And then I want to know why we care about it. Do these people defend spontaneous generation or the biogenesis? That's what we're going to work on for the next few days. And then we're going to do a gallery walk to find the 3 most important items for each of those scientists. We'll finish up with this short video on chemical evolution. As you're watching this, consider which scientist you want to study and sort of the direction you're going to take this project.
Stated Clearly presents, what is chemical evolution? Scientists have reason to think that the first living cells on Earth came about through a natural process called chemical evolution. What is chemical evolution? How does it work? And how is it different from biological evolution? To answer these questions, we'll start by first dissecting the terms and then look at an example of how chemical evolution can take simple molecules and organize them into complex structured systems similar to those found in living cells. The word evolution simply means change over time. Biological evolution deals with changes in things which are able to reproduce. Living creatures make copies of themselves. The change over time that we see in biological evolution is not just random change. Oftentimes, it is adaptive change. Populations become better able to survive and reproduce within their environments. When conditions are right, biological evolution can even drive a species to develop brand new characteristics and abilities. For this to happen, biological evolution typically requires three conditions: reproduction, variation, and selection. Let's see how this works. Many species of holly have smooth-edged leaves. English holly, however, is covered in spikes which protect the plant from deadly predators. How do these weapons first evolve? Well, when a holly plant reproduces, its offspring often show random variation. They are slightly different from their parents and slightly different from each other. In a forest filled with grazing animals, individual plants which happen to be harder to eat than their siblings are more likely to grow up and have children of their own. Nature, simply by being difficult to survive in, selects who gets to reproduce and pass on their new traits and who does not. In this case, mutations which simply caused the veins of these leaves to extend past their edges gave rise to a brand new weapon. The discovery of biological evolution was an incredible breakthrough in science. It explained how new complex traits and abilities develop naturally in living things. The problem is, biological evolution depends on reproduction in order to work. Reproduction, however, is an extremely complex process in and of itself. This begs the question, how did reproduction first evolve? To try and solve this mystery, many scientists are looking into chemical evolution. Chemical evolution refers to changes in things that need not be capable of reproduction. Examples could be individual molecules or entire chemical systems. A chemical system is a group of molecules that interact with each other. Molecules, structures, and chemical systems almost always evolve or change over time, but they often evolve towards simplicity. Solid iron corrodes into rust when it comes in contact with water. Proteins break down when exposed to too much heat. If simple chemistry is to give rise to something advanced enough to reproduce, there must be situations in which chemical systems can grow in complexity, form new structures, and gain new functions. In order for this to happen, reproduction, which is needed in biological evolution, can be replaced with a much simpler process: repetitive production. On planet Earth and all throughout the universe, powerful natural events take place in regular cycles. The heating and then the cooling of day and night, the repetitive eruptions of volcanic geysers, the rise and then the fall of ocean tides. These events repetitively produce or give birth to new molecules and chemical systems. These products increase over time and often develop new abilities as they interact with their environment. Let's see an example of how this process works. This here is a special molecule called a fatty acid. It's a collection of carbon atoms, hydrogen atoms, and oxygen atoms, all stuck together in a specific pattern. Fatty acids are one of many complex molecules that living cells use inside their bodies. They build fatty acids with atoms they get from their environment. Scientists used to think that living cells were the only things able to consistently build fatty acids, but check this out. Lab experiments have shown that if simple common gases, carbon monoxide and hydrogen, are heated up with minerals like those found in the Earth's crust, a variety of complex carbon molecules, including fatty acids, begin to grow. Living cells are not needed. This can happen naturally in underground chambers, heated by the Earth's magma. As pressure builds, these molecules can belch up into pools of water, where a simplified version of natural selection then takes over. Most particles blasted into water will either float fatty acids are suspended in warm water, growing in number as the cycle repeats. When fatty acid concentrations are high enough, they bunch together, automatically self-assembling into a stable ball. This happens because water molecules are attracted to the oxygen heads of fatty acids, sort of like a magnet, but water repels their oily carbon tails. When fatty acids pass near each other, their tails are pushed together by water, eventually forming a ball. As fatty acid collections continue to increase, they join together to make large skins. If fluctuations in these skins happen to make the edges touch, water forces those edges to fuse together. The end result is a stable hollow container, similar to the membrane or skin of a living cell. These containers have a brand new ability. They can trap other molecules inside, acting as an entirely new environment for chemical evolution to continue working within. It's important to note that these membranes do not qualify as living creatures. They can't reproduce on their own the same way living cells do. That said, the development of these membranes, along with many other molecules and chemical systems that scientists have observed, demonstrate an extremely important principle. Chemical evolution can give rise to new characteristics and abilities. Because of this, scientists hypothesize that under the right circumstances, chemical evolution could give rise to systems that are fully capable of reproduction. If they are correct, this would bridge the gap between chemical evolution and biological evolution, demonstrating that chemistry can indeed give rise to life. Scientists at the Center for Chemical Evolution and other research groups around the globe are working hard to test this hypothesis. The main difference between chemical evolution and biological evolution is that chemical evolution can produce new characteristics and abilities without depending on reproduction. Because of this, chemical evolution is being investigated as a possible cause for the origin of life. I'm John Perry, and that's chemical evolution stated clearly.
All right, so back to your assignment. I'll post this up on the board so that you have the directions here, but this is our project for the next few days. On the last day of the assignment, when everyone's finished, we'll do the gallery walk. So it'll be important for you to have enough information that we can take notes from your scientist and your scientist experiment. Thank you very much. Good luck, guys.